Q&A function at the bottom of your Zoom interface. May I now welcome Ms. Nalini Ravichandran to deliver her presentation on ground vibration study in Karstic Limestone Formation for controlled blasting work in Klang Valley. Ms. Nalini has extensive working experience in controlled NATM tunneling method and had previously served as the committee member for the tunneling and underground space divisions of IEM for 2018 and 2019 sessions. Please welcome Ms. Nalini Ravichandran.
A very good morning, everyone. My name is Nalini. I've been working as site engineer for MIT projects since 2016, which involves site-based experience for Eaton tunneling method. And I have experience of working together to cater few technical problems like cavities, sudden water ingress, and ground settlement for underground works, which is pretty common for extreme karstic limestone formation. I have Bachelor in Civil Engineering from UTB and completed my Master's in Geotechnical Engineering in January 2020 from UTM. So my topic for today will be involving about ground vibration study in karstic limestone formation for controlled blasting works in Klang. So before we start with the presentation, let me display a video for you. Based on the video today, my topic will be focusing on ground vibration study in karstic limestone formation for controlled blasting works, especially for highly populated locations like Klang Valley. Vibration study plays vital role in order to reduce the effect to the surrounding. This study involves the blasting data collection from karstic limestone formation at Klang Valley, which is used to establish the relationship between the peak particle velocity and scale distance technique. So I will briefly explain the relationship between this PPV and also scale distance, which is will be used to establish the K and V constant together with the blasting parameter studies, which is important for optimization and also for safety concerns. So for my presentation today, the outline will be starting from the introduction, problem statement, aims and objective, scope of study, literature review, methodology, results and discussions, conclusion, recommendations, and final references. As we know, blasting activity is dangerous. In some situations, it can cause disturbance to public in surrounding. This is because the shockwave that travel in a form of energy through the ground can cause damage to the nearby structures or properties, we will say. Besides that, flying rocks and also air blast is extremely dangerous for the public safety and also to the nearby structures. The prediction of peak particle velocity is vital for us to secure the safety of the surrounding people and also to shield the surrounding building. As per our current practice, the blasting designers are using the site constant of K and V values as of 1140 and -1.6 respectively. As we can see, controlled blasting regardless of the rock type. So the predicted peak particle velocity data shows that higher reading as compared to the measure, which is raised double on the accuracy and the stability in using the constant doublet from the Australian standard. So what will happen is the designer will reduce the explosive amount and the PPV to suit for any particular control blasting works. So this may lead them to reduce the explosive amount to suit the PP desired for any particular controlled blasting work. So the main objective today is basically for us to study and found the suitable site constant K and D value which can be used in square root rule scale distance equation for Karstic limestone and Klang Valley, and also to establish the relationship between the blasting parameters which involve maximum charge per delay, number of holes, hole depth, power factors, PPV, and Karstic formation. So for the scope of this study is basically just control blasting operation for Karstic limestone formation at Klang Valley, and I only use USBM, which is United States of Bureau of Mines equation, to develop the K and D constant by using the scale distance method. Okay. As we know, this is the Klang Valley geological map. It consists of two major ground formations, which is the Canny Hill formation and also the Karstic limestone formation. One can classify this Kuala Lumpur geological area as the alluvium overlying of Silurian age, which classify as extreme class. So, Karstic limestone in lime, it's found through the chemical dissolution of the ground, which groundwater that circulates around this limestone bedrocks. It is totally opposite of the canning formation, where it is totally unpredictable, dangerous, especially for foundation construction near the Bulatan Kampung Pandan area, where it is near the Gombak and also the Ampang fault line. These two fault lines exactly at the intersections between the limestone and also the Hortonum formation. So when these two points, in the intersections, so the groundwater, the Gombak fault line basically encouraging the groundwater to seep through towards the limestone formation. When these two fault lines encourage the water to seep through to the limestone formation, limestone, it is basically, as we know, it is soluble. So what happened is it encouraged the extreme formation of the Karstic limestone. What happened is the carbon dioxide from the atmosphere, it mixed with the rainwater to form the carbonic acid, and it dilutes the carbonate element in the limestone. So the karstic feature forms rapidly via the bedding planes, joints, and also the faults through the gravity flow of the water to the ground. So the karstic limestone formation is totally opposite of this canny hill, where it is totally unpredictable and dangerous, especially for foundation construction near the Bulatan Kampung Pandan. So this is what you can see, particularly in a karstic limestone formation. You can have a lot of cast windows, caves inside the waterbed, and you have a lot of valleys. So it's very, very unpredictable for extreme cast. And unfortunately, Kuala Lumpur geological data shows that, especially as the Bulatan Kampung Pandan, it's been classified as the extreme cast. So if it's extreme cast, we have a lot of caverns, you have a lot of pinnacles, we have a lot of overhangs, troughs, and flutters. Okay, next we will talk about the contour blasting. So basically what is it? Because contour blasting is designed to lower the vibration and noise which is conducted in a highly populated area, or which we is also called as contour blasting work. So you can see here we have covers. It's a closed area, so no people are allowed to be around there. And we reduce the flying fragments by adding more covers on the blasting. So this is what it is, control blasting. Basically, this blasting, they have few mechanisms for the vibration to travel. So when the S wave is created, the P wave encounters the geological change, and the S wave only travels through solid material. When a P encounters a geological change, the part of the energy reflected back, and then the remaining energy transmitted in a refraction. So this is how is the vibrations of mechanism. Okay, next we have maximum charge per delay. Okay, what is maximum charge per delay is the maximum amount of expressive charge that we detonated in one delay or per interval of blast. The maximum charge per delay can be obtained by this formula by W over D over ds in bracket. So in general, these are the blasting parameters that will be used for the blasting works. All these parameters are equally important in terms of different functions. Okay. For example, for a simple logic, maximum charge per delay involves the amount of explosive that we're going to use. So which means the more explosive you use, the higher the vibration of, or we call it as peak particle velocity. So blasting hole, whereas should be, if it is parallel to the free face, okay, what we call a free face means we have blasting area, then we create a small free face here, so that when this is being detonated or charged, when the vibration travels, so it will create easy path. Okay, so when the vibration travel, it will create the easy path for this side of one side of the rock or the rocks to collapse. So in terms of that, we will get a better production of blasting works. And blasting hole that is parallel to the free face expected to reduce the peak particle velocity. Bench height is important to control the flying fragments with the bench height. It's very important for us to control the flying fragments. And at larger burden, the role of stress wave reduces the fragmentation when it's transferred to the surround. Therefore, the vibration increases. So from the parameters, then we use the scale distance to find the, and also the maximum charge per delay to find the K and B constant from the graph that we formed. So we form the graph by using a log to leg scale for scale distance versus PPV versus the scale distance. Then we will obtain the R square and we put it inside the formula to get the K and B constants. So for methodology, we only obtain data for 2 different locations and focusing only at the extreme cast area nearby the Belatan Kampung Pandan. So for blasting method, we have first of all the drilling the blasting holes, then we have the chargings. After we done with chargings, we cover to control the flying fragments. Finally, after the explosion is done, the blasting is done, then we collect the data from the vibrometer. So this is the overall summary of it. First, we collect the data. Once we collect the data, we have monitoring data and also the blasting data. We analyze the data. We clean the data, which is sometimes due to the instrument itself. We may find some of the data is not useful, so we clean the data. We conduct the statistical study, and we compare with the blasting parameters, and also we use it to find the gain. So basically, now coming to the main point is, based on the results or the research outcome that I get, it found that the constant that we get from the Australian that we have been using is 11404 K and B is negative 1.6. Whereas the actual constant from the blasting monitoring data, which by using the K and B constant that I obtained, is K is 26.74 and B is negative 0.801, which means based on the calculation that I conduct for one of the sample, it shows that the vibration values is actually higher as compared to the one that we are using. So you can see here the peak particle velocity and the PPV and the maximum charge per delay. Apart from that, I done some studies on the blasting parameters. Sadly, that the blasting depth and the actual PPV doesn't show any correlation. It's a bit of scattered data. Same goes to the burden. Spacing is slightly. Powder factor as well. Bench height. Maximum charge per delay. Number of blasting pools. So what I can see is that the prediction equation produced by the AS21872 that we are using currently is not suitable to be used for karstic limestone formation in Malaysia. The predicted ground variation gives higher value as compared to the actual recorded blasting data. This means the amount of explosive cannot be optimized, as the blasting operators will reduce the explosive as to make sure that the PPV does not exceed the permissible level as given by the authorities, whereby in real situation, they can use the higher amount of explosion to get higher blasting protection for better rock fragmentation, and also it will be under the limit of permissible vibration limit. So what we can see is the actual vibration is actually much higher by using the constant that I found from the studies. Then the vibration is higher, and it means when we use the small amount of explosive, we need to be in term of certain tolerance. So when our data showing higher PPV in the design itself, we will reduce the explosive. When we reduce explosive, definitely the blasting production will be lesser. So we will require more frequency of blasting operation to get the fragmentation that we require. Therefore, the optimization will be less. This is why the K and B constant is important for the optimization. So this is the conclusion that I explained just now. It's no longer suitable because the predicted ground vibration value gives higher values compared to the optimized. So we cannot optimize the data, which will reduce explosive to make sure that PPV peak particle velocity does not exceed the permissible level. Therefore, in real condition, bigger amount can be used for us to get a better rock fragmentation. So for recommendation, I would say the research should be continued for control blast research using different blasting technique to study on the peak particle velocity data and also the blasting parameters influence with the maritime data. Of course, we can't compare this with just few places, which means probably we should conduct more studies with different blasting formulas so that we can compare and get the best data. And also we can compare the blasting data in Kuala Lumpur Canyon for further study with our Karstic limestone formation and see the differences. So that's all the presentation for me today. That's reference. Thank you.
Thank you, Ms. Nalini. Ladies and gentlemen, we will adjourn for 10 minutes break.